Hey, what's up, guys? This is Chung here. So today, LeetCode number 1878, get biggest three rhombus sums in the grid. Um, so this one, okay, you're given like m times n integer matrix grid, right? So a rhombus sum is like a sum. Basically, it's rotate. It's a square, right? Which is being rotated 45 degrees, right? Something like this. And the rhombus sum is the sum that the element this square, right, passed. For example, this green one, right? So the sum is like this. Is this one, all the green color cells, right? And as you guys can see, so we could have like many like rhombus sums in this grid. Oh, and one more thing. So a cell itself can also be a rhombus cell. Basically, the size is 0, the area is 0. But this rhombus sum can expand. Okay, and you just need to return the biggest three distinct rhombus sums in the grid in the descending order. Right, these are just minor stuff. And if there are less than three distinct values, return all of them. Right. So for example, we have this kind of like 5 by 5 grid, and among all those kind of rhombus sums, we have this three to be the top three biggest, right? And this is another one, and so this one is like an edge case. Basically, we only have this one row of grid, and all the possible values, they're all 7. That's why we only return output 1 7, right? And so the constraint is pretty small, right? 100. So this one, I mean, nothing fancy, Actually, so this one is more like an implementation heavy problem where, since this constraint is pretty small, right? I mean, it's only 100, which means we can just simply basically try to find all the rhombus square, rhombus square, and then we calculate the sum for each of them, right? And yeah, so I mean, there are pretty many ways you can find all the rhombus squares here, right? So for me, the way I did was I fixed the top one. Basically, I fixed the top corner, the top one, and I tried to expand. I tried to expand this rhombus to both sides until either left, right, or bottom has reached the border. Then I stop. Right, and then with this kind of 4 like coordinates, I can calculate the sum for the square. Right. Similarly, I starting from here, and I just calculate this one, and then basically calculate it row by row. With this kind of fixed border here, let's say we have this fixed 4 borders here. The way I calculate the sum for this square is starting from row 1, and then we left is equal to right to here, right? And then every time I decrease the left by 1, and I increase right by also by 1. So we have this one, and I continue to do it until we have reached the border, the left border, and then I change it to increase the left by 1, and I decrease the right by 1 until I reach the end. That's how I calculate the sum. I'm pretty sure there are like other ways to do it. And yeah, so that's it, right? I mean, since no quite fancy stuff, logics here, so let's start the implementation then, right? So I have this one, m equals to n, grid n equals to the length of this one, grid 0, right? So for I in range of m, right, and then for j in range of n. So basically, I'm looping through the top border here, and for each of the border here, I will try to expand the square starting from here. So which means I have this so left equals to right equals to I, right? That's the left and right border. So J, yeah. And then down, I use down means the bottom, right? DM means I represents the bottom, gonna be the I, because I will be expanding from here. So while L is greater than 0 and R is smaller than n minus 1 and the D is smaller than n minus 1, right? So and then I do a sum. I do a calculate sum of calculate, assuming we have this kind of helper functions, right? So we're passing the 4 borders, so left, right, up and down. So up is I, right? Down is D. And then I decrease L by 1, right? And then I increase the R by 1. And then for the bottom one, I increase it by 2, right? Because every time when we increase the size by 1, basically we'll end up having +2 bottom coordinates, right? And then for the final answer, since we only need like top 3 biggest one, we can have like priority queue here, or you can just use array. It's fine. If the length of the priority queue is smaller than 3, right? And since we need the distinct values, I can simply do a check. So if the sum not in the priority queue, right? I do a heap queue dot heap push of sum, right? Else, if we already have 3 values here, then also still we need to check. We need to do this one, and second one is this, and the sum is greater than the priority queue of 0, since the first one in the priority queue means the smallest among the 3 ones. So right, if we find like a bigger one, right, and then we can just replace that. Heap queue dot heap pop, right, and then heap queue dot heap push of sum, right. And then in the end, right, we just return the 3 values. But since we need to return it from in the descending order, right, we can simply sort it, right. Reverse equals to true, right, and then return the priority queue. So that's the main logic here, and the only thing left is this kind of helper functions where to calculate the sum, right, given like 4 borders, left, right, up and down, right. So we have sum equals to 0, and then since the way I calculate it, I starting from the top one, and I try to expand the left and right coordinates, and then right. So that's why at the beginning, the column 1 and the column 2 is going to be the L plus right divided by 2, right? And I have like expand flag here, that can tell me if I should expand the left and right or shrink it, right? So for row in we already have R here, so for row in range of so up is smaller, down is bigger, right? So that's why we have a up to down plus 1. If C1 equals to C2, which means there are like either top one or the bottom one. In this case, we only need to accumulate once, right? So we have row and column 1. Else, we summarize both of them. Okay, right? And then I do this. So if C1 is equal to L, which means if the C1 has reached the border, then it means we need to start shrinking, right? Then the expand, I'll set expand to false in this case, right? And then later on, so when the expand is true, then I do a C1 minus 1 and C2 plus 1, right? And else, when we start shrinking, then we do a C1 plus 1 and then C2 minus 1, okay? And then just return the sum. So I think that's it, right? So if I run the code here, accept it, right? Yeah, there you go. It seems like I just write it pretty fast, but when I try to solve this one, I had like a few edge cases. I also made some mistakes. For example, the this U and D, right? I mean, I was using the D and the U plus one because by calling the up and down, I thought, by looking at the name, I thought the D is smaller than U, but in fact, it's like U is smaller than D, yeah, something like that, right? And so for the time complexity, right? We have I'm times n here, right? So this is a n square, and then this is another while loop here, right? And this is what? Another n here, maybe? And then here to calculate this one, we have another n here, I think, right? Another n. So is that like n to the power of 4? Yeah, I think it's not that much because so the more the more we're going down, the less we'll have in this while loop, and the less we'll have in this calculation. So I don't think this one is like as big as the n to the power of 4. I think it's more like n to the power of 3, maybe. Yeah, I'm not quite sure about this part, but anyway, I think that's not the key thing for this problem. Actually, maybe that's why a lot of people downloaded this one, because there isn't too much like thinking process for this problem. It's just like trying to implement it, right? Find a way to calculate all the rhombus, right? The sum, and then get the top 3 one. Yeah, anyway, I think I'll just stop here, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.